Okay, so now we've seen kind of how neatly vectors and one-forms fit together using the definition which I introduced last time, which I'll just simply restate here quickly. We have that an arbitrary vector, when it acts on a function, and now just remember briefly that functions are zero forms. We have the definition of the action of this vector on the function. We use this kind of angled bracket notation to denote this one form df, which we remember is defined using this exterior derivative on the function. And so this thing is a one form, it's a map, it just wants to eat something, and it eats the vector. So this was just a definition that I introduced, and we showed that it was consistent, and then we began to see how we can interpret these objects, particularly this df object, as essentially the gradient of this function f. If you remember, I said that we could have just done something like that and represented our vector as this kind of nabla operator, which, if you remember, is this kind of partial derivative operator that you've probably met in vector calculus. We usually like to call this the gradient of the function, but now it actually makes more sense to talk about the gradient as being this thing df. And we're going to see shortly how we can have a nice kind of visual way to represent this df. So we hopefully should have a kind of fairly intuitive picture in our heads of what vectors look like. Essentially they're arrows, and now as we kind of move into this more advanced differential geometry, we should be starting to realise that vectors, well, they are arrows, but those arrows are kind of arising from derivatives in some way. So we view vectors as being the tangents to curves or smooth functions. And so everywhere on a function we can always kind of produce this sort of velocity-like vector. This is our function f. And so we saw how this vector is produced. Essentially, well, we can express the vector as some kind of combination of components with these derivative basis vectors, which are just going to act at each point to kind of produce vectors that are pointing along the coordinate axes. If, say, we have our coordinates x1 and x2, the partial derivative basis vectors just point along the coordinate axes. So, vectors intuitively are arrows, but now what do these one forms look like, and how can we have a sort of nice intuitive visualization for essentially what one forms are, like we have this kind of nice intuition about vectors being arrows. So the kind of visualization which I'm going to introduce now, I should note, is just really intuition. It's not anything too concretely well defined, and it doesn't apply necessarily in all of the cases. But essentially the view that we take is that, well, a vector is some kind of arrow, and now we're going to view a one form as kind of being the normal plane to that arrow. So let me just draw what I mean. So if we have some kind of vector v, and then I introduce now a one form omega. So we view the vector as kind of being an arrow, and the one form we can view as being this kind of stack of, well, in this case, lines. If we had, this is in a kind of two-dimensional picture. If this was in 3 dimensions, these would become kind of stacked sheets or planes that this vector is then piercing through, and so on in higher dimensions. So what do these planes essentially represent? Well, the best way to kind of view this is to just look at essentially the coordinate basis one form, dx, And so I'll just draw this one form. Let's say that this is our x-axis, and now this, which I've drawn here, this stack of sheets, a one-dimensional stack of lines essentially, is the one form dx. And now what do we mean by this? Well, essentially we mean the coordinate separation between these two sheets is going to be dx. So this is the point 0, then this first sheet is going to be at the point essentially dx, and then so on. If we're at the point x, this is the point x plus dx. And so of course dx is just now here being used to kind of represent this infinitesimal distance. We'll be able to get a concrete definition of dx, use it when we define a few more things shortly, but for now just kind of think of it intuitively as this infinitesimal separation here. And now this one form which I've drawn, essentially we can now use to measure the lengths of vectors, or to not lengths yet. They'll become lengths when we introduce the metric, but for now it's going to be something which we use to essentially extract components of vectors. So what do I mean by this? Well, if we now introduce a vector into this picture, let me just realise that this is going to be, or just now make this a two-dimensional picture. So we also have some y-axis. Let's just call this the origin. And so we have our one form dx. It's just this stack of sheets separated by an infinitesimal amount, dx. And now let's introduce a vector. Okay, so this vector which I've drawn here, v, just erase this for now. So I've drawn the vector v, and now what this one form is essentially going to do, well, we're going to interpret its action on this vector v as essentially, well, we look at this vector and we essentially count how many of these one form planes have we pierced through with this vector. So the vector v goes from the origin up to here, and we've essentially passed through two of these one forms, dx. So now what this essentially means is, or what this is measuring rather, is essentially how much of this vector extends along this x-axis, or it's just essentially going to extract the x component of this vector. So obviously I've drawn a really, really tiny vector here. It's only extending two kind of infinitesimal dx amounts. In practice this will be a much, much longer vector, and we would do this counting of how many surfaces have been pierced by the vector using some kind of integral. But just intuitively in this picture for now, the vector, when it's eaten by dx, is just going to kind of, well, it's going to produce a real number when a vector, or when a one form eats a vector. We're just mapped to a real number, and that real number is essentially going to be the number of dx's that we pass through. So this is 0, this is 1, and this is 2. And so what this coordinate basis one form has done is that it's essentially measured the x component of this vector. And now that's how we should view the action of one forms on vectors, is it kind of decomposes each of their individual coordinate kind of components, and it just turns it into a number. And so the simple one form dx is just going to essentially extract the x component of any vector. So just as I've drawn on here as well, I'll just quickly note I drew the one form dx. I could have equally drawn another one form, say dy, which this distance here corresponds to the infinitesimal dy, and now we would count okay, well this vector here is maybe going to have components 3 in the dy direction, or when measured by the one form dy. Okay, so now let's have a more mathematical statement of this fact. So first of all, let's just introduce onto this picture. I've already drawn the one form basis. Let's just quickly draw our vector basis. Remember, if these are our coordinate axes, then our vector basis is just going to simply be 2 little vectors that point along each coordinate direction. So we're going to have this first vector, partial derivative with respect to x, and then this second vector, partial derivative with respect to y. And now these squares, or these one form lines, they should be intersecting at squares because the amount of our coordinate in dx and dy is essentially the same. But now what we can see is that these coordinate vectors, essentially when we measure them against the one forms dx and dy, well, the coordinate vector dx simply just has length 1 along the x-axis and 0 along the y-axis, and similarly for dy. So now this is just a kind of pictorial representation for an identity which I introduced in the last video. Essentially, when you contract any coordinate one form, so with any index, with any coordinate basis vector, unless these indices are the same here, essentially with dx1 and the partial derivative dx1, this is going to give us a Kronecker delta, essentially, unless we're looking at dx and the partial dx, or dy and the partial dy. Essentially, this is now just the formal statement for this kind of picture which I've drawn here, that whenever we have the partial derivative basis vector, it only points kind of normal to a single one of these components. We don't have any component of the dy basis vector pointing along the dx direction, say, otherwise this contraction would be non-zero for the x and y components, say. But hopefully this is clear just from looking and thinking about this picture, and now we can see that really the one basis vector, our basis vector points along our coordinate direction, and then our one form is just a kind of normal plane to that basis vector. So we're going to use this heavily throughout as it simplifies a lot of our calculations and is really how a lot of the calculations are actually computed. And I'll just give a really quick example now. We've already seen the really simple example of when we just simply contract a basis vector with a basis one form. That's just this formula which I wrote here. But now let's just write down formally this example with this orange vector which I drew here. So I have to kind of cheat a little bit and know in advance what this vector's components are going to be. We can see from this picture it's going to have 2 and 3 component. So I could express this vector v as essentially 2 dx plus 3 dy. That's one way I could have written it. I could have also just written it as a kind of column like that and just left it implicit that this first element is the element with the x basis vector and so on. But it's just kind of clearer to write it in this way. So this orange vector we're going to now plug into the one form, essentially the coordinate basis one form, dx mu. And we're going to just compute it using this expression here. So essentially we're computing dx mu v, and if we just substitute this expression, first of all we're going to realise, well, because the one form is linear, we can split it, and split this plus, and essentially we're going to be left with Okay, so I just substituted in v is 2dx plus 3 partial y, and now used essentially the fact that this angled bracket is a linear map. I can just take the result of adding an input. It's the same as mapping the two inputs separately and then adding them together afterwards. So that's essentially what I've written here. And now we have to realise, okay, well, this is a linear map. I can just pull those scalar numbers out front. And now I just have to realise, okay, well, this bracket expression is just this identity which I've written here. This is only going to be non-zero for the dx one form. So essentially, writing the answer up here, this is going to be 2 dx plus 3 dy partial y. So what we can see has happened, we've inserted the vector into our coordinate basis one form, and it's extracted both of the components, and then it's just going to add those components together and give us a real number. So if that calculation kind of reminded you of the dot product, it really should, because, well, as we're going to see when we go on to discuss the metric in a bit more detail, we're going to see a very similar calculation to what we just computed, and we're going to essentially realise the dot product is just an example of this one form contraction, or just the action of the one form on a vector. We're going to see the dot product is calculated very similarly by essentially taking two vectors, turning one into a one form, and then contracting the vector and one form together. And so we're going to see a lot of calculations like this, and we're going to realise that they're made incredibly easy by this identity here. Okay, so in summary then, we've introduced a more kind of intuitive picture for one forms, or how we should visualise one forms, and we've seen that we can view vectors as being kind of arrows that point in directions that are produced by derivatives, and now how we should view one forms is essentially being the normal planes or normal surfaces which are going to be pierced by those arrows. And so we saw a simple example of how we can construct simple one forms using these coordinate one forms. And we can see how we can use these fairly simple pictures to do calculations just on the picture, simply measuring components of vectors using one forms. And then we saw how we can translate that fairly informal pictorial calculation into a concrete expression, and it's all really connected through this identity here. So now I just want to really quickly add something on and mention something about this gradient. Essentially, this picture I drew here using just the dx one forms just kind of gives us this fairly simple grid. Well, it kind of represents the coordinate grid of our coordinate system, or it's really the coordinate grid that we use to measure our vectors against. But now, this is just the coordinate basis one forms. Remember that any arbitrary one form is going to be some now linear combination of our coordinate one forms. And we're going to see that this is just essentially kind of going to spread and stretch, or even turn this grid into some entirely other kind of curvy linear grid. And it's just going to simply depend on what these components are. They could be just simple numbers, or could be entire functions of the coordinates. And if it's, let's say, some kind of function of the coordinates, it's going to produce some kind of non-linear grid like this. Say, for example, we could have the one forms in polar coordinates, and they're going to produce similar to the picture that we have over here, but they're just going to be one forms that measure against the polar coordinate grid. And now finally, just to mention about this gradient, a nice kind of way that we like to visualize this gradient. If we have some, let's say, some function that's changing in a two-dimensional function, so we have some kind of f of x, y. We might consider taking the gradient, or now we should rather express it as the gradient 1 form. What this is going to produce is it's going to look something kind of like a contour map for essentially how this function is varying through space. So it might look something like this, and we should interpret these lines as 1 forms, and they're going to kind of come with their dual, which is the vectors at every point. So these kind of lines which I've drawn, we usually take as representing the kind of level sets or the level values of this df gradient function. And now the little vectors which I'm drawing, they're going to be essentially the values of the gradient vector field. So these are going to be the nabla f's, or essentially just the components of this gradient 1 form. Because remember, the gradient 1 form is, all it is just a 1 form with some set of nonlinear, potentially nonlinear functions as its components. And now these components are essentially the components of the gradient vector, but we usually refer to this 1 form now as the gradient.